Hello, my name is Danny Franklin and I am an SCPD student up here in Seattle. Today I'm going to talk to you a little bit about my final project, Connect Mesh Generation and Viewing. First I would like to discuss a little bit about the motivation of my project. The first motivation is for creating 3D models of scenes. It is often difficult to generate or reproduce 3D models of different scenes. My project aims to provide a way to generate 3D models of any general-purpose scene. Second, my system works to provide a way of intuitive viewing of models. Oftentimes it is difficult to get a feel for how your model would look to a user when navigating with the keyboard or mouse. This system uses the Kinect to track your head movements and adjust the scene as if you were looking at it. Overall, these can be combined to create a 3D webcam so that it feels as if you are in the room with the person. Here is a brief summary of my project. First, I use a Kinect 3D sensor to capture the depth of the scene. Next, I recreate that scene as a triangle mesh in OpenGL. After the mesh is created, the 2D image from the Kinect is applied to give it color. Further, this system allows meshes to be saved for further use. If you'd like to use a mesh you already have, standard OBJ files can be loaded for viewing. Lastly, we use a Kinect to adjust the image based on your head positions. Here is an overview of the technical approach. The Kinect provides us with a 3D point cloud with X, Y, and Z coordinates for each point in meters. It also gives a 2D RGB image of the room. Lastly, it gives an estimate of the location of a user's head in X, Y, and Z. The technical goals of this project are as follows. First, filter the point cloud to eliminate noise. Next, convert that point cloud into a triangle mesh, and filter that mesh to find different object segments. The next step is to fill holes in the background created by depth shadows. Once the mesh is built, the 2D image is applied. From there, we want to allow users to save and load meshes and use the Kinect to view the scene intuitively using one's head. The first step in my project was 3D point cloud filtering. The point cloud generated by the infrared Kinect technology, while impressive, is very noisy. Many points are returned as points at infinity. First, we need to filter these points. Many of these points come at the edges of objects. As such, they can be filtered using a mean filter of the surrounding points. Only valid points that are not estimated at infinity are considered in this average. Unfortunately, this results in an almost entirely connected scene. Imagine draping a blanket over the entire scene. This is not desired behavior and will be remedied in the next step. The next step is to convert from a point cloud to a triangle mesh. Many techniques already exist for doing this conversion. A very popular one is doing Delaney triangulation. In 2D, this is easy to imagine. Basically, this technique arranges the triangles such that no circle formed by the connection of two vertices as its circumference has another vertex inside it. This can be extended to 3D by using spheres. This results in a well-connected, well-oriented graph. Next, in order to keep close objects apart from far ones, a threshold is applied to the triangles to ensure that objects that are far from each other are not connected. The next step is coloring the scene. The 2D RGB values can be mapped onto the vertices of the mesh. Because the two cameras are different, a camera calibration is required to map from one to the other, which is a complicated process. Luckily, the Kinect SDK supplies a coordinate mapper class to aid in creating this mapping. Though it does have issues when objects are close to screen, it is suitable for this use. The last step is to do the Kinect head tracking. The scene is altered as if the viewing surface is a window into the 3D scene. As the user moves his head, the scene is adjusted accordingly. GL frustum is used to create this effect. Imagine moving the camera from left to right while leaving the frustum the same. In practice, the opposite is done. The left, right, bottom, and top limits are shifted along with the entire scene as the user moves their head. This creates the appearance of it being a window into the scene. I encountered many difficulties in this project. First was interfacing with the Kinect and learning its API. I was using the new Kinect version 2, which is more powerful and accurate, but has an SDK still in developer preview. There were not very many examples of its use. To begin, I tried to use C++ as we have in class. However, the Kinect API in C++ is very complicated. I eventually decided to switch to C#. This required porting a lot of code and also using a C# wrapper for OpenGL, called SharpGL. There were several subtle nuances between SharpGL and OpenGL, and that required even more learning. Another difficulty was the color mapping. Originally I started working toward calibrating the two images, but found it difficult to do, and even more difficult to do accurately. Upon finding the coordinate mapper class, I decided that though it had errors, it was not worth reinventing the wheel. Another difficulty is in the frame rate being poor. I believe this is due to the C# wrapper or interfacing with Kinect taking a lot of resources. This frame rate issue limits the amount of real-time processing I could do, as it's already quite slow. Another big problem is with the background shadows. As you will see, behind a user there is a shadow where the Kinect cannot see. This is unfortunate, but in the webcam scenario users won't deviate from very much from the same perspective the scene was captured at, so it isn't that bad. Working to close this shadow was done, but it is very difficult. Edges can be extended into gaps, but as the number of objects can have any number of orientations, it's difficult to do this. To close gaps, I suggest loading the mesh in a 3D modeling program and manually closing them. Now we're going to see it in action. Here is me showing that it is a triangle mesh that is regenerated using the Kinect and the point cloud. Next, I've tilted it, rotated the camera so that you can see that it is in true 3D. This also lets you see what I mean by shadow, as you can see behind me. Also, feel free to be jealous of my great moves. This is a lit shaded version of the mesh, so you can see as I move the camera around the scene, it's being shaded. Lastly, this is the Kinect webcam portion in action. Obviously there's a shadow behind me, which you can see, but you can also see how it is moving in a 3D manner as I adjust my head. In the webcam scenario, instead of a stationary person, this would be a video. This part shows a 3D scene that doesn't have any objects in the foreground, so you don't get any shadows. If you look closely at my bed, you can see as it moves around that it is in fact 3D. There are many places that this can be applied in the future. I think I have shown how this can be combined to make a sort of 3D webcam. Additionally, these techniques can be extended to get more information by moving the Kinect around to get a more complete picture. Lastly, this can be used to create a virtual window in an office or home to see a beach scene or a cityscape or even a live feed of somewhere important. Thank you for listening, and feel free to contact me at the email listed here.